Hello everyone, we are at Infinity Hyperloop, a team of 25 undergraduate students at IIT Delhi. I am Raj and I am the head of brakes department. Today we will be presenting our design progress on the braking subsystem. So when we started out, uh, when we were designing, we were looking at all the existing kinds of brakes that are out there. And the most commonly found brakes used in existing systems that we found were frictional, aerodynamic, and magnetic brakes. And in magnetic brakes, we had permanent magnetic and electromagnetic. So before making a design decision on which kind of brake we'll be going forward with, we decided to at least list down what are our requirements and what is the problem statement we're facing here. So we looked at our requirements. The propulsion department gave us the input that the maximum velocity that our pod will be facing is around 100 kilometers per hour. And in the 1 kilometer track, we'll be having an approximate 300 meters of braking distance. And since there is an upper limit on the weight of the pod at around 230 kilograms, we also wanted the braking system to not exceed at least a mass of 30 kgs. Now, we wanted the system to require as low maintenance as possible, and it should also be scalable. It should not just be suited for the first version of our pod. It should be suited for future versions as well with very little modifications, and the future versions would obviously be running at higher velocities. And for contact braking systems, the competition requires the Brinell hardness to be less than 85 HB. This is because it should not scratch the aluminium track, which is made up of aluminium 60626. So this was also an important input for our material decisions. Note that unlike disc brakes, we didn't have to worry too much about temperature, since in disc brakes, one point repeatedly passes a braking caliper or a magnetic brake. And in that case, we have the issue of the disk overheating. But in this linear sort of systems, we pass a point on the track once and that's all. So we don't have to worry about heat generation. So moving on, I'll be explaining the choice we made. Aerodynamic braking systems were ruled out because there was little air pressure in the tube. So like it is not possible to slow down the pod. To have a completely contactless braking system was also not possible, since magnetic brakes produce significantly low drag forces at low speeds. So we decided that we will need frictional brakes. Now one might argue that at speeds of 100 kilometers per hour, frictional brakes could do the entire job ideally. But since we have scalability as a core requirement, we also thought of introducing magnetic brakes, since at future versions we will require higher velocities at which the frictional brakes don't require a lot of maintenance, as they undergo a lot of wear and tear. So finally we settled on a hybrid frictional and magnetic brake. Now I'll explain the technical specifications of the magnetic brakes. So our magnetic brakes use permanent magnets in a hallback array configuration. Now, first, we had to choose between permanent magnets and electromagnets when we were choosing our magnetic force generating mechanism. So we chose a permanent magnetic configuration primarily because our battery management system would not be capable of providing power to a linear induction motor and an electromagnetic brake at the same time. So we went ahead with permanent magnets, since they require they require no power from the BMS. So the Hallback array configuration is essentially to produce more magnetic flux at a with requiring the same amount of mass. So if you would look at the image in the top right corner, you can see two images. The one on the left is a standard magnet having equal flux on all sides, and the one on the right is, let's say, a magnet of the same mass, but it has a higher flux density on one side. These Hallback arrays are essentially made by connecting a lot of magnets, where each subsequent magnet has a magnetization direction 90-degree rotated as to the previous magnet. And this leads to a high flux concentration on one side, so we can have this side facing our track to generate higher eddy currents and hence higher drag forces. The material we decided were neodymium magnets, essentially NdFeB arrays made of neodymium ion and boron. We have not yet decided on the grade. We'll be explaining more of the material selection in the subsequent slides. Now we will be using the top flange of the I-beam for eddy current generation. You can see on the bottom right the image that shows where the eddy currents are being generated, and we will be using electric actuators. So now I'll be explaining why we went ahead with this particular choice of actuators. When we were starting out, the most three common actuators that are out there are hydraulic, pneumatic, and electric actuators. Now, hydraulic actuators were ruled out because of lack of autonomous usage, because we need something that presses the mechanism manually. So we essentially had to make a choice between pneumatic and electric actuators. We have listed out the different parameters in our comparison table. We can see that pneumatic actuators are generally fast, as you just release the air pressure and it forces the actuator very fast. And we also have the ability to control speed by controlling the airflow in the valves, but it has a very high mass due to the compressor, and this is why we went ahead with the choice of an electric actuator. Note that we were aware of the fact that a lot of teams use a reservoir with and they fill in compressed air, and they store this compressed air such that like enough amount of compressed air such that it runs on the 1 kilometer track perfectly. But we did have scalability as one of our core requirements, and such a system is not commercially feasible where we have one reservoir and that same reservoir, like we can't have a set amount of compressed air. We need an active compressor generation mechanism, and hence we would need a compressor. Now, the electric actuators that we have chosen provide feedback as well. So they also tell us the actuation distance as to how much the actuators have actuated. This input is then provided to the navigation and control department, so they do not have to attach sort of additional sensors to determine how much has the brake actuated and where it is right now. Now I'll be explaining why we chose the neodymium magnets as our materials for the magnetic brakes. Now you can see here that there are four images, and we have sort of compared SMCO magnets, NdFeB, alnico, and ceramic magnets based on the magnet cost, operating temperature, corrosion resistance, and magnetic strength. Now you can see that the SMCO and NdFeB magnets are far stronger than the other types of magnets. So we'll be focusing just on these two while making our decision. And we can also see that the neodymium magnets are able to provide a higher magnet strength at a lower cost. They are also readily available at many stores and any grades that we want, and readily available in various shapes and sizes. So this choice was quite obvious, and we went ahead with choosing NdFeB magnets. Now I'll be explaining the simulation and the modeling that we did for our magnetic brakes in COMSOL. So we made sort of a 2D model in which there was a brake with external magnetic flux and a conducting track. And in this, we generated a curve of track force versus velocity. So the conductor was given some velocity and we found the curve for the drag force. So what you see on the right are sort of two equations and two graphs. The upper equation and graph corresponds to a study that we read, and it is an analytical solution. When a magnet runs over a conducting track at a high speed, they have modeled the track's inductance and resistance and solved for the current that will be produced. And from the current, we can get the current density and hence the drag force. So the upper graph corresponds to the analytical solution that we get, and the lower equation corresponds to the numerical equation that COMSOL uses to solve for the eddy currents. So here Bi is the magnetic flux of the magnet that is sort of passing over the conductor, and B is the magnetic flux generated due to the eddy currents. So given Bi, we can solve for Be, and what you see with the sort of the blue line is the drag force versus velocity curve generated by the numerical solver. Note that the magnitude is negative since the drag force is negative, but if we reflect it about the x-axis, we can see that the analytical and numerical curves correlate quite nicely. Now, this proves to us that our model is valid, and since both shows a similar drag force versus velocity curves. Also note that the drag force decreases exponentially as the air gap increases, and this was also shown by both of the analytical solution and the numerical solution. So now we have the model that works, and we are sort of trying to give it different designs and different grades, and trying to decide upon the grade of the magnet, and trying to finalize the design of the magnetic brake. So now let's move on to the frictional brake. I'll highlight the technical specifications of the frictional brake. What you see on the right is a CAD model of the brakes, and so you can see that these brake pads sort of slide on two guide rails, and they can press against the top flange of the I-beam, similar to the magnetic brakes. However, here the actuation distance is in the Z direction. The actuators used will be electric, as same as the magnetic brakes for the same reason. We'll be using organic brake pads as our material, and we are also using two guide rails to ensure that it counteracts the moments generated due to asymmetric drag forces. So when we have sort of different drag forces at different points on the brake, it will generate a moment about the guide rail, and we don't want the brake to rotate at that point. So we have two guide rails to ensure stability of the structure. Now we have chosen organic brake pads here. Like, we were mainly deciding among organic, ceramic, and semi-metallic brake pads. We chose organic as they provide slow wear and tear, and there are a wide variety of materials in organic brake category that have Brinell hardness less than 85 HB. So it was quite easily available, and like good for manufacturing reasons as well. Now this is the current like stage of the design. In the future, we want to make the design mass efficient. So we are analyzing the stresses and strains at different points on the brake, and we are trying to remove material when a lot of stresses are not there. The simulation model that was presented was two-dimensional. The graphs in COMSOL were generated during using a two-dimensional model. We want to make a 3D simulation model so that we can validate our designs even more. We also want to make a control system that can control the actuation distance to change the magnet overlap with the track, so that we can control the track force easily generated by the magnetic brake. And we want to make the design modular with maximum similarity between magnetic and frictional brakes, so that in the future, if we want to increase the amount of magnetic brakes and decrease the amount of frictional brakes, we can easily do so. Thank you. We would like to thank CHC for presenting us with this opportunity. We are now open for questions and suggestions.
Thank you so much, Infinity Hyperloop, for that presentation. We are now open for questions. Just as a reminder, you can either type the questions in the chat box and I can read them out for you, or you can switch on your camera and mic and ask them right away.
Hello.
Yeah.
Yes, I have a question. So I just wanted to ask that what is the exact mechanism by which you are actuating the brakes, the friction brakes?
We are using the same electric actuators. So the electric actuators are essentially, like if you have noticed, there is a screw type mechanism on which there is a motor which rotates, and there is like a structure that sort of goes ahead and behind depending on the rotation of the screw.
So if I'm
So these are like
understanding,
standard electric. Sorry.
if I'm understanding this correctly, it's a lead screw mechanism.
Yeah, sort of.
Okay.
So these are like the standard electric actuators that are readily available.